A typical application of the logistic equation is a common model of a population growth, where the rate of reproduction is proportional to both existing population and the amount of available resources, as well as the number of predators around. The general formula for a logistic function looks like this, where C here refers to 50,000, A refers to 1,000, and K refers to 0.5. And note it's not minus. The minus is not part of the K value. Typically, you might be asked to find the initial population of wasps. And since T is the time here refers to initially 0. And so in our equation or function, we will substitute 0, and we'll find that it's 50,000 divided by 1 plus 1,000 e to the minus 0.5, and we'll substitute 0 for the time here, and this will result in 50,000 over 1 plus 1,000, which gives us an answer of 49.95. And as these are wasps, we'll assume that that's going to be 50 wasps. And please note that you can find the initial population of any logistic function by calculating C over 1 plus A. A logistic graph will always look like this, having an S-shaped look. As we are always interested when time is equal to 0, we can ignore the left-hand side. What we want is this point here, which indicates to us the initial population. This kind of function, you'll also notice that it starts to level out. There is a limit to which this graph will not go beyond. And this particular level is C, which is 50,000. And this would be the number of wasps that this particular environment can sustain or support. Now, to show that the population is always increasing, we need to show the gradient is always increasing. We need to calculate the gradient function from the original function. Our logistic function is rearrange these functions so it's all in the numerator. And now we are able to differentiate this. This is a chain rule, and so we're going to need to now differentiate what's inside the brackets. Multiply the 50,000, the 1,000 and minus 0.5, then e to the minus 0.5t over 1 plus 1,000 e to the minus 0.5t squared. And it's obvious that the denominator will be always greater than 0 because it's squared. And the numerator is always going to be greater than 0. So the derivative function must always be greater than 0. Well, this means that our function, logistic function, is always increasing. And hence the number of wasps are always increasing, although limited by 50,000. If you're asked to calculate the time of the inflection point of PT, it is very easy. All you need to do is use. So T is equal to ln A over K. This is ln 1,000 over 0.5. Use your calculator to find out This is 13.8, which is equivalent to 14, and we're dealing with weeks. And this is the fastest rate of increase. And it occurs at 14 weeks. So the point of inflection occurs using this formula. How I got to this formula, I have made a video previously on the point of inflection of a logistic function where I show how I got to this formula. You may want to view that video if you log into my channel. And if you'd like to receive more videos, then please like this particular video and subscribe to my channel. Thank you.